samosa. So, oh, he's coming. Oh,
Everybody, run. You mean as I was? Oh, you came here first time. So if you can, then you should your grades. No. So I'm encouraging everyone to check Astroph new papers every day. You can also sign up for the class, then you get credit. This is a test. Yeah. You're welcome to sign up. Yeah, since you're here. So. Okay, good.
so what they will offer? Sorry.
Okay. I was a bit worried that Terry might start without me. Because yeah, the important one sounds very right. In the past, they came in a little base, like 2 or 3 minutes. Then they just started the class. Because they're really doing a class without me. I look really sad. But that's okay, that's good. Okay, so
Yeah. So today I will be presenting our paper, which is already which we are currently writing. It is not complete yet.
good.
So here in this paper we have taken micro lensing of binary compact objects with mass under 1 solar mass, the combination of M1 and M2. So here the main thing is that we have defined functions as a combination of the lensing, which is capital Fij, which will give us the orientation of the lens, and delta Tij, which will give us the time delay. So following that, we will calculate the Einstein angle and what is the radius of separation, and from there we will get two equations, which is this one. This will be the time delay equation. So it is a function of capital Fij, because the delay in the time will be depending upon the length which we are getting because of the binary objects. So this is like the first of a kind. Earlier they were working on the error estimate. No one has directly used the equation to solve the parameters and got the values. So this is called like a closed form inversion method, in which we have taken a function of Einstein angle capital Tij and the geometric factor, and have calculated the values of the mass and the capital D. So following this, this is the phase difference which will be given by the scintillation method. Equation number 21. Delta phi 2 by lambda delta D. B will be the like what effect it is giving to the medium. So for like how it will look. So this is the lensing, how it should look. It is currently in progress, ray tracing method. So here the binaries will rotate, and this is a magnification which we'll get. And for a real like image, it will be similar to something like this.
Wait, if all these are points,
Yes, sir. So these are the binary objects.
so these are from binary.
Yeah. Yes.
Okay. Are these greenish kinds lens?
Yeah. Yeah. Yes, sir. So from background we'll get the FRP, and because it is
Here, before we sign an example, what did you assume for the simple FRP?
yes, I will show. Like this. So like FRB is at the position of the star, yellow star here.
Okay,
So
it's nice. So can we talk FRB usually points was much smaller than the resolution of the telescope.
mhm.
But then here, it looks like your result
Yeah.
you have the sign to measure. I wonder what's the size and it didn't really make a result on the telescope.
So we can, because we are using the scintillation method. Yeah. So the separation will be reduced.
Okay, dimensionless, then say, for example, sums.
Yeah.
Put some
Real units. Yeah.
yeah.
Okay. So that I will add. So in this case, sir, we are capturing the images at the red dots. Total four. Yeah.
The plus minus minus.
This one. Yeah. Yeah.
Okay.
Yeah. So these are the compact objects here. So we'll capture these four images from here. So we'll calculate the delta T from here and the capital Fij. Like how the lensing is changing the geometry here. Like here. So, see, it is not very clear, but here we'll get four images, like one here, two here, three here, four here, and one in between.
Yeah. Okay.
Yeah. So from this we'll get capital Ij, and we will we'll follow this equation. This one, equation 36. The combination of the capital M mass, which is the sum of two M1 and M2, and capital D, which is ds by ds dr by ds dr. So following both, we'll calculate the Hubble constant using this function. So in this, we are getting around 70, an error percentage of 1.5.
Error is 1.5.
Yes, sir, 1.5.
That's very good.
Yes, sir.
Okay, so you put some example number and it.
Yes, I simulated a sample FRB, a toy model.
When you don't put it's really.
Yes, sir.
Just what was not the same.
Yes. And so mu, I, and j are the images.
What we
Yeah,
lens.
single element. Yeah.
So one time for look at the BD.
Okay.
The estimation was showing many FRBs, right?
Yes, sir. No,
Just one
right now I'm using only one FRB.
one just
Yeah.
family.
Yeah. Because of lensing, it is creating a delay of multiple peaks. But FRB is only one. If we take multiple event, then I also have that in account, so we can calculate it using like 25 number of events or 26. Because in the earlier paper they have taken 24, 30 observable, and they are getting an error percentage of 1% here for Hubble constant.
Yeah.
Yeah. So
You get even smaller.
yeah, 0.4, 0.5.
You mentioned that.
Yes.
Very nice.
Yes, sir. So one more thing, sir. Like our formulation is very accurate because if we are making the S closer to zero, then we are getting the exact result as we should get for a single mass lensing.
So what is this?
The separation, yeah, yeah, between the two mass. Like if we reduce the value of S to zero, then we'll get the exact same result that we should have be getting for a single mass. Yeah, yeah, I'm getting that exactly. Both are exactly same. Delta factor, delta T.
So how many some see this figure? See the
Yeah,
it's to the right.
yeah. So I will make the plots good. It is like pre not correct. So the GY function is for the binary one. Okay, function. And yeah, so here if you take S as zero, so both we are getting exactly the same. So it is behaving like a point massless and not for a binary thing.
Not sure what
Yeah, I show one again.
or
No, color is like just for demonstration. Yeah, these two. So like this is for a single mass. So yeah, so in this plot and compared to this plot. So like this one we are having 2 masses here, M1 and M2. In this case, we are having only one. So if the equation which we are using, so in that equation, if the value of S is 0, then those 2 mass will coincide. So we'll get like a single mass. So all the results which we should get for a single mass are exactly same for binary. So it will act as a validation.
Okay. Okay, so is everyone okay? Who understood what he said? Who has no idea what he said? Okay, so great. So let me, explain a little bit. So Rodney is constant length. It's then so we hear the FRB, right? The FRB we heard yesterday. That's very different. It's very different. And then here's the length. Length. What are you assuming? Primordial number, things like that. The primordial. And then here, Rodney is here, right? Rodney is here. This is the end. And then the light is going to come. Usually length is like this, right? So gravitation means so you see twice in this way and this way. So the burst is to be 1, 2, or something. But then, so this is already written by there's one thinking about what if primordial black hole is a binary facing each other, right now. And then what? Signal difference.
Yeah.
So instead of can you show some examples? So instead of so length like 1, 2, he was showing a 4. The red one is the length.
Yeah.
The last one. Length.
Yes. 1, 2, 3, 4.
So you actually get this C or 3. Yeah, so we go it's binary. And then we can have one there. So he can measure this time difference. So one signal comes first, and then the other one comes later, right? So there's a delta t time delay because the path length here is a little bit different. So one comes first, shorter one comes first, and then longer one comes later. So there's a time delay, and then we can measure this. Okay, and if you measure this depends on the size of the universe, which is determined by the Hubble parameter. Because if the universe, this whole set is bigger, this also bigger, right? If this whole set universe is smaller, this time delay is going to be smaller too, right? So by measuring this delta t, you can measure Hubble parameter h0, which represents the size of the universe. Then, so now talking about, can you explain? You get a better constraints of Hubble parameter of error is 1.5%. Why you get a better constraint than single length?
Yeah. So because so we are using algebra for this. We are not assuming the error here. Because in this case we are using
Okay.
so the delta will be reduced. Like if here we have industrial meeting, so it will present like if here we have delta y, then earlier we'll get delta x. So from Earth we can capture the signals both properly here. And so in the earlier paper they were using error estimation, percentage how much error they are getting in each observation. And from there they are calculating H naught. But in our case, what we are doing is that we have taken 3 functions completely unrelated method. We are not taking any uncertainty here. We are taking a function of delta Tij, which is this lengthening, what we are getting here. Yeah. So it depends upon phi, what angle it is making here. Because it is moving, like the binaries are moving here. So it is a function of phi. So phi is a function of capital Fij.
Yeah.
Which means geometry, how it is moving. Same thing. Now this is a function of related to Gm, which is the mass of binary black hole M1 and M2. And this is a function of H naught. Yeah. Yes. So from here we can directly calculate the Hubble constant without any error. And earlier they got it as 6%, but we are getting at 1.5 for a single event. And this was for 30 events. So maybe it will go to like 0.2%.
We have more.
Yeah, more events. Yeah. And I will use 25, 30.
Yeah, yeah. That's good. Yeah. This is very nice.
Yes.
Where you can have the you can solve the solve tension if it's 0.2%. Yeah. So this is okay. I have a big question. So how does the mass of the binary and the separation between the two black holes, how does that affect the observed time delay?
Because from the understand.
Sorry?
What is the angle between the what is the angle is forming in the distance?
Is that theta?
Yeah.
Okay. So how does that affect delta tau? The time that delay between.
From the propagation of light rays here.
Yeah. Okay.
Like when we study the light ray will pass the use of a more broader lens and delta T will change.
Okay.
Like this. Simple.
Thank you. Yeah.
Yes.
Okay. So, but then so we can know the math of the math of the concept, right? So these are parameters.
Yeah.
Okay.
Okay, any more questions? How about the delta T? You know, that typical time scale, like millisecond or something. Oh. Okay, because it's like if you separate like two peaks here, it's still separate. It's just like two signals come very late. But if they are not too late, so it's look like interference or something. So it's close like this one. Oh. Mhm.
But usually they are because the separation is too large. If you take if you take 0.5 to another factor, the delta T will be very fast. So like usually you get delay. In order to reduce it, we use simulation method. Like this is very good. So delta T, delta X both are interrelated.
Yeah.
Time.
Sorry, just one more question. This is like uh probably really out there, but do you know if we would see similar effects in the delta tau if instead of two primordial black holes orbiting each other, we had like some other compact object like a new like binary neutron stars or something? Would we see a similar effect in that? Okay. Okay, that was it. Is the mass, yeah. Okay. Right. Okay.
Okay. So yes, it's time to go on. Thank you. Thank you, Swati.
Um, can people see this? Okay. Okay, good afternoon, everyone. This week I want to present a paper titled Quasar Radiative Feedback May Suppress Galaxy Growth on Intergalactic Scales at Redshift 6.3.
And so the main question of this paper was these scientists wanted to understand if quasars can suppress star formation in near and metal line cooling in nearby galaxies. And they think that this could be suppressed by the heating and ionization of gas in these nearby galaxies due to quasar luminosity. And so for this paper, they use this this quasar, which has a funny name, J0100 plus 2802. At this redshift, and the reason they use this is because it's one of the most luminous quasars at this high redshift. And so their observations were all made. They were observing the O3 emission lines from galaxies near the quasar at approximately 20 co-moving megaparsecs from the quasar. And the reason they used O3 was because it's not affected by radiative transfer, unlike the Lyman H alpha, which is, it has high effects. It's highly affected by radiative transfer. So they wanted some other emission line that could be used to detect star formation that isn't prone to this radiative transfer effects. And so the first figure here is just like what this is like the raw data, if you will, the raw surveys. They use this Sapphire survey and this other Eiger. I don't know how to pronounce that survey. And so they detected a bunch of different what's it called? Bunch of different galaxies. This black cross right here, I don't know if you guys can see that. That's the location of our primary quasar. And so they detected a bunch of galaxies that produce this O3 emission in the background, which is highlighted in orange, foreground in green, and some other I guess nearby in red. And so let me see. Yeah. So here are the specifics of what the three different redshift samples produce. Their final catalog after some data manipulation and some error manipulation was that they ended up with 24 galaxies in the foreground, 22 in the near, around 6.3 redshift, and 17 in the background samples. And so these are some, I guess, data manipulation graphs. But the real important one is this one right here. I should explain that the main thing that they were analyzing was like the O3 emission, right, which has a emission wavelength of, I forget. I think this is 5 point. Yes, this is O3. This is the O3 luminosity, and this is the UV luminosity. And so essentially what they were doing is they were comparing the O3 luminosity with, they made a ratio between O3 luminosity and UV luminosity. And the reason why they did that is because the O3 emission shows star formation, while the UV emission shows, like, I guess, background, and it shows emission of stars that are already there. And so they were detecting, the ratio was basically exemplifying new stars versus stars that are already, new star formation versus stars that are already there, or old stars. And so they were measuring that ratio, and then they compared it to this what's it called, ionization field. There was a little bit unclear to me how they produce the ionization field. I didn't quite get the math that was done all the way over here, so I apologize for that. but it's essentially, yeah.
The quasar luminosity on there. From the quasar, so a function of distance.
Yes. Yeah. And so this is like the important like final product right here. So essentially what this is saying is this is showing the ratio luminosity with respect to distance from the quasar. And so we can see that the luminosity is the O3. This ratio is actually decreasing the closer we get to the quasar. So on top right here we have distance in units of co-moving megaparsecs, and so the closer 0 would be where the quasar is, where our object is, and so we can see that the closer we move to the quasar, the less O3 emission luminosity we have. And so that can be, this is showing evidence of like less star formation going on near this this quasar, right? And so, yeah, and so it says right here that there's a mechanism that suppresses nubular line emission without immediately affecting stellar continuum. And so what that means is that we can see it right here in this graph, that the UV emission, no matter the distance from the quasar, stays pretty constant. And so the quasar is not affecting any previous like star luminosity, and it's not the quasar is not affecting UV luminosity. It's only affecting O3 luminosity, as we see here that the O3 ratio is decreasing the closer we get to the quasar. And so this can be due to like I said at the beginning, some sort of radiative feedback from the quasar acting on the gas that is like disrupting the ionization or cooling conditions in these star forming regions. And yeah, I think that was pretty much it. Here I just highlighted some of the three main findings: that there was a decline in the ratio between O3 and UV luminosity. The closer we get to the quasar, and there was a weaker trend along the line of sight. But also something that I should mention, that the red ones right here show our main these red squares show the J100 data that we got, and then these blue hexagons show the same data but from another nearby quasar. And so this is evidence that this is expressed in a more widespread this effect is shown in a more widespread area, not only in this quasar. So more quasars can, if we find more quasars and analyze their ionization fields and the O3 emission lines in those galaxies, they would show this. They could hopefully show this similar trend of less star formation nearby quasars in the nearby quasar region. Yeah, that's pretty much it.
Thank you, Andrew. Any questions?
Who understood what he said? Get the question? Okay. Who understood what he said? You okay? Who is not okay? Okay. My drawing time. You wanna see my drawing here? It's a drawing class. So here, here's the paper. For you to greater, like angel, right? It's here, right? And then he is emitting strong UV light, evaporation UV, right? So if you're sitting close to this guy, you get dead. Maybe it's too much. So usually galaxy, these galaxies are emitting O3, right? Star forming. But then galaxy is gas, so usually there's a gas, right? This is blown away, say for example, because of the strong UV. So it cannot emit O3 anymore. But then if you're far away, if your galaxy is far away, then UV light is a little bit weaker. So here here it's weaker, so O3 can survive. So as a function of distance, the O3 gets weaker and weaker. And then that's what they found in this paper. So this may be they're arguing, okay, near the quasar there's a strong UV light, so galaxy cannot do a star formation. No star formation. No O2. No O2. O3. And here far away, star formation is okay. Okay, O3 is okay. So that's what this paper is. Do you know? So this is Reggio 6.3, right? Do you know who did this at Reggio 6.4? Almost 10 years ago. It goes up a little. It will go on, go to G.
A
Here. Good flavor is this. Good flavor is this. Wow. 17. More than 7 years before that.
Wow.
Should be big.
Maybe I should read it. Maybe I should read your paper.
Yes, please. You can introduce some of the paper. Yes.
Wait, so was this a bad selection? Was this a bad selection of paper?
So check, right?
Okay.
Of course, I'm here. Generally. So this is generally.
Okay.
So they can do the emission line. Now using the super test. Without therapy. But we have 64. Even better.
Even higher than she. That's pretty cool.
Any more question? Is that okay? Okay. First question, okay.
So if there's no more questions, so let's move on to Musa.
Here, I want to, practice my talk. So because I'm going to a conference next week, and then I thought it's also good way to introduce Terry's paper because I'm going to talk about Terry's paper here. Is it? Okay, so can I really like I'm really giving options for us for don't unfortunately this is not working. If I run out of power, it's working. Okay, so today,
Yes.
so now introduce my students, super junior students, series. Hey, but before starting, I want to thank everybody, including just all the who were engaged during institute. Okay, so then we will stay searching for planet 9 using our personal. Maybe you all know this story about the discovery of the Neptune. So back in 1846, more than 80 years ago, so these guys found this is Uranus. Uranus's velocity sometimes gets faster and sometimes gets slower. And then they speculated, okay, there might be another planet here, which now we call Neptune. And then Neptune sometimes pull Uranus to speed up and sometimes pull down to slow down. So there may be another planet. And when they calculated where is the Neptune's position, and then they predicted it's here, and then this guy got it, pointed a telescope there, and then it was there. Neptune was there. Maybe you know the story, right? Yeah. people call it Neptune was discovered by Ken and Hayden. It's a great story, right? It's a serious trial. Maybe everybody learned this in the class. You learned this in the class? No? They don't teach it in the economy department. They do. That's good. Please remember, they're now having toothpicks in the 21st century. And then, okay, nowadays, we know this, there's a lot of small objects outside of Kuiper Belt, Neptune. It's the Kuiper Belt object. These are small bodies, these are not planets, maybe kilometers to up to 100 kilometers, something like that, these small ones, many of them, thousands. And then in 2004, they found a new one, a very distant Kuiper Belt object called Sedna, and then they calculated its orbit, and it was like this. So Sedna was orbiting like this, and it was weird. Its orbit is elongated. To make objects actually orbit elongated, something need to perturb it. Some gravitational force is needed. And then you might think, okay, it's Neptune. Neptune is big, but it's not touching Neptune's orbit. If it turns like this, orbit is touching Neptune, it's easy to explain. Oh, Neptune made it elongated. But it's not touching. So Neptune cannot do this. So who did it? That's the question. And I not just said that, but then people find more elongated distant kind of objects. For example, this one, Leliac Honor. Orbit is elongated, not touching Neptune. And then this Biden, this orbit is elongated, not touching Neptune. So who put up these objects? And even more, nowadays, a lot of type of other objects have elongated orbit, not touching Neptune. And then the second mystery is expressed in orbital space. In simple words, here's the solar system, Neptune, and it's only on one side of the solar system. There's none on this. Why? It is weird, right? If it's random, it should be everywhere. No? So what's going on? So if you look at in this movie, which I should skip a little bit. Yeah, so these orbits are almost on a piece of paper. It's clustered. Only in this line, there's nothing. This is very weird. This 99.9%, this is like when you see many people are looking one direction, the same direction. This doesn't happen randomly. I mean, when you see something like this, there is a reason. There's a reason, some reason. So it's the same in this case. Then in this case, the most plausible reason is most reasonable dynamical solution is there may be okay. So this is randomly 99.99% impossible. So there must be a random solution, a dynamical solution. And the most plausible reason is the presence of giant planet on the other side, which we call planet 9. If there's a giant planet on the other side, this planet perturbation can kick out small bodies on this side of the solar system, and only small bodies can survive on the other side. And so, perfect explanation. In this simulation background, so here you start, and then in the simulation, this is a long movie. Say, if you notice, so this is a planet, right? They did a simulation. And then sometimes you notice the object here on this side disappear. That's because they are kicked out by planet 9. But the object on this side can survive because the orbit is not overlapping with planet 9. And at the end of many years simulation, see, the object here gradually disappears, right? And the only object on this side is surviving, right? Then at the end of the simulation, it looked like a clustering that we saw. So there was still planet 9. We need to find it. Okay, and then this is the destination parameter predicted the presence of planet 9, the mass is maybe 5 to 10 solar mass, several hundred AU with some inclination, there may be a planet mass. And here I want to remind you, the planet 9 bit, the mass is 5 to 10 solar mass, so it's like as massive as Uranus or Neptune. It's a giant planet, not like Pluto. So this is the Earth and this is Pluto. Pluto is just 1/4 of our moon, even smaller than our moon. So we're not talking about this small object, we're talking about this giant planet. So this situation, I think you remember the Neptune discovery story at the beginning, theoretical prediction, point the telescope did. We are in a similar situation as in 1846. There's a theoretical simulation predicted there. We just need to find it, right? So the hunt is on. A lot of people in this field are looking for planet 9. Yeah. However, it was not successful so far. So a lot of telescope, PSI, Y, Subaru, DTFB, and also a lot of optical survey didn't find any planet 9. Why? Because it's faint. Because this several hundred AU, optical magnitude is 26. Then positional uncertainty is 100 optical degrees. So even the large telescope nowadays, it's very difficult to survey 26 magnitude in that kind of very large area of the sky. This is very difficult. So we need to find, okay, optical, not in, okay, maybe. Have you seen Netflix? No? Exactly. This I recommend this journal. Anyway, so if optical is not working, what should we do? Planet 9 is a low temperature black body, say 30 Kelvin, then it's bright in infrared. Well, do you know what it is? It's Jupiter, and it's bright in infrared. Same, planet 9 should be bright in infrared. So then, light need to go back and forth, reflected sunlight, right? But then thermal radiation, black body infrared, is coming only one way. So decreases only the power of the distance to the -2. So that's the voltage. Okay, so if it's a black body, it peaks at far infrared, 100 micron. Okay, so we need to search planet 9 at 100 micron. And then who has a far infrared all-star telescope? Do you know who has the? Do you know far infrared all-star have a telescope? You don't? Do you? Do you know who has it? Yes, I have it. I have it here. This is our team's far infrared all-star telescope called Akari. Our telescope, well, this is by the way launched movie. We did all-sky survey like this. We launched a space telescope and we did all-sky survey. I mean, this is a map we made. This is the all-sky far infrared map. So somewhere on this map, there's a planet 9. Big discovery is in this map. Can you find it? Is it here or here? No, these are much. But somewhere you zoom, it's there. So we need to find it. So that's Tom's hardworking graduate students. So look at what Terry is doing here and to search. But how am I doing in the time? Sorry, went over 10 minutes. Terry did not just use Akai, but he combined previous all-sky infrared satellite model launched in 1983 and combined moving object from this data to this data. That's what Terry is looking. But then, okay, Akari is not telescope. Can it detect it? Sensitivity is enough. Actually, it seems enough. So up to 600 AU or so, Akari can detect the planet 9. Okay, so sensitivity is good. So how about orbital motion in 23 years? So from 1983 to 2007, Akari orbital motion, it depends on the distance, but something like 70 miles per minute. Okay, so Terry needs to find a pair of objects separated something like 70 minutes. Okay, then this is what Terry did. So Terry specifically, he specifically made a single scan catalog. That's the only good thing Terry did. So Akari did Postgres survey like this, and the public catalog, so it did many scans of Postgres. But in public catalog, it's combined all scans, and then they remove moving objects. So you cannot use public catalog to search your planet. No, you need to have a catalog from single scan to find moving objects. So that's what Terry used. And then he searched for objects that are detected multiple times on the same day, but then a few months later, that object disappeared because it's prime time is moving slowly, so it can be detected on the same day, but then not months later. So that's these objects Terry found. And then remove known sources, and then try to find pairs, which he did the same thing for iris, and then pairs within 70 minutes. And he found 13 objects. He found 13 pairs within 70 minutes. But then most of them are just garbage, some not. But there was one object, one candidate remained, which is this. Oh, no, not this.
You don't know how.
Sure. I never recorded them. Then, this object in IS unit was here in 83, and 2007 Akari image is here. So according to Terry's story, this object moved from here to here in 23 years between them. Okay. And then we published this in a paper. Terry published this. It's accepted. So congratulations to Terry. And then to our surprise, Terry was interviewed by many. This was featured by many magazines. So this is Science Magazine. This is ABC News. This is Yahoo News in Japan. And also, thanks to Tetsuya-san, this is news in Taiwan. So that was good. Okay, maybe I should skip this job. And then, okay, maybe I cannot skip this. So, when Science Magazine requested that the interview was Terry, they sent an email like Sunday. And then I was not checking email on that particular Sunday. I went to marathon, as some of you know. And I was not checking email. And then Terry replied it by himself, replied to Science Magazine, so like this. Unfortunately, I usually have a class and a group meetings on Monday, so I am not available to have an interview with you. So, okay, for Terry, my group meeting and my class is more important than interview with Science Magazine. Which do? Classes are important. So, detections are not enough to decide orbits. To decide orbit, we need minimum some detection to decide the orbit and I see if it's really prime time. So we carry the prime to some level forward to the energy camera and then to do the follow-up observation, right? So is that your plan? Okay. So this is the summary. I keep up the summary slide, and then how minutes did I take? Okay, I need to show them. Okay, you have to practice because I am over 3 minutes. Okay, well, thank you very much. Any questions? Yes, you can go.
Why did Terry decline?
Reasons.
Like reschedule? Well, that's not why. Since article says.
Right. Yes, so I sent email to science, but please could you reschedule the interview? They scheduled interview on Monday morning, and Terry was sleeping. And then I had to ask Gary to go to Terry's dormitory and then knock the door. Terry, wake up, Terry, wake up.
What do you say, is it?
Yeah. It's
So, if other candidates were rejected, visually these are like you interpret it visually, or how
Yeah.
you classify that these are methods, these are different.
Actually, that's the visual section. And then, because to show that
Which one? I only have the good one.
just two words. Yes, slim. On a candidate 23 years, we still see the IRAS disposition. So it means that they are not moving source. Yeah. So that's why we reject accepted. So here you can see in 1983, we see the detection here, right? And then after 23 years, it disappeared. Yes. So that's why we consider it should move from IRAS position to Akari position. But other candidates is still at the same position after 23 years.
How did you know that that new object in Atari was the same object in?
Yes, we propose the possible pair between IRAS and Akari. And to determine if they are the same object or not, we have to conduct the follow-up observation. Yes.
Okay, if no more questions, maybe we round up, huh? So
Yes.
we should, yeah.
So thank you, Thomas. And let's. We need to decide who will present the paper next week, next Tuesday. So, Darian, right? We need two more volunteers. Okay, so what's your name?
Yeah.
Lee. Okay. One more. So, Sean. Okay. Okay, so next Tuesday we have B, Samalima, and Darian. Yes. So thank you everyone for joining, and see you next week. Bye bye.
There.